All right, guys. Welcome back. Last week of school, last week of finals. Um, yeah, 5 questions, work and energy, part 2. Let's just get into it. So, first question: as a ball is thrown straight up in the air, what is happening to its potential energy and its kinetic energy? Okay, so a ball is thrown straight up in the air, right? I don't know if I have to draw a diagram for you guys, but straight up in the air. Okay, so what is happening to its kinetic energy and its potential energy? So pretty much what's happening is the potential energy is going to be increasing and the kinetic energy is going to be decreasing. So why is that? So the way I look at potential energy is the potential for energy to happen without like an external force or whatever. So when we're throwing the ball straight up in the air, we're creating the potential for energy to happen, right? So the higher it goes, the more distance it'll have to fall, right? So the higher we throw the ball, the more potential energy we'll have because it has to fall a greater distance, right? And likewise with the spring, we increase potential energy by compressing the spring or stretching the spring out. We're creating the potential for that spring to bounce back to neutral, right? Because that takes a lot of energy. And then kinetic energy is, you could think of it as the energy that it takes to create that potential energy. So yeah, this can be easily demonstrated by their equations. So we know the equation for kinetic energy is 1/2 mv squared, and then potential energy is mass times gravity times height, right? So in this situation, as we throw our ball straight up in the air, it's constantly decreasing in speed, right? So as our velocity decreases, our kinetic energy is also going to be decreasing, right? So as the ball is going up, our kinetic energy is constantly decreasing because of that. And then in here we have the height of the ball, right? So as the ball goes higher and higher, we're creating more and more potential energy, right? So because we increase the height of the ball, we're increasing potential energy, right? So then when it's coming down, ball's up here, coming down, now what happens to potential energy and kinetic energy? Cool. So now the ball is going to be speeding up, right? So our kinetic energy is increasing, and it's going to be losing the height, right? It's losing the potential energy. So essentially, that is what's going on here. Okay, so number 2, what is the elastic potential energy stored when a spring is stretched 25 centimeters by 450 Newton force? Okay, so we want to find the potential energy, right? So we know this equation for potential energy, we're talking about a spring, 1/2 kx squared, right? So we know the distance it was stretched by, right? So we know x, we don't know k, and we want to find potential energy. So how can we find k? That's the missing variable that will give us the answer, right? We know this other equation, which is perfect, and it utilizes force, right? So force equals spring constant times x. So we are given the force it takes to stretch the spring. So if we know that it's stretched 25 centimeters, which is 0.25 meters, right? And you use a 450 Newton force to do that, then we can get our K value. And in this case, the K is 1,800 Newton meters, right? So now we have our K value, we have our spring constant, and we just plug this in to our potential energy equation. Cool, and you solve it, and you get 56.25 joules. All right, so it's just sort of like a system of equations. You have 2 unknown variables, use a different equation, which you know both the variables, and you can plug it in. Like I said, systems of equations is what we're utilizing. All right, so number 3, how much work is required to stretch a spring from 3.8 centimeters to 6.5 centimeters, given the spring constant is 150 Newton meters. The spring's natural length is at x equals 0. So we know this equation for work, where it's work equals 1/2 k delta x squared. Okay, so we can use this equation, right? And that'll give us the work. So, because we have all the variables here, we have the change in displacement of the spring or position, and then we have the spring constant. So we could rewrite this equation to look like this, and make sure you rewrite it like this. All right, so k, x final squared minus, I'll do it this way. So I'll do that. Okay, times x initial squared. Right? You don't want to write it like this, where it's w equals 1/2 k times x final minus x initial squared. You don't want to write it like that. So make sure you don't do that. So now we have our equation. So work equals 1/2 150 times the final length is, converting to meters, 0.065 minus 0.038 squared. And then when you solve it, we get our work, which is 0.209 joules in this case. Right, good. All right, so Archer pulls back the string on her bow to a distance of 70 centimeters from its equilibrium position. To hold this string at this position, it takes a force of 140 newtons. How much elastic potential energy is stored in the bow? Okay, so again, we're trying to find potential energy, that equation, and it is acting sort of like a spring, right? This string on this bow. So we can use this equation. And what do we know? So we know the distance, we know the force, just like before, right? Like the previous one. So we know the force, we have a force equation that can give us K, because we don't know K, so we want to find K. So first thing, find K, 140 equals K times 0.70. And then we get our K value, 200 Newton meters, and then we just plug it in, right? It's pretty much the same problem as before, just, the string is acting as if it were like a spring in this case. So 0.70 squared. All right, and then when you solve it out, 49 joules. That's what you get. All right, last one. The elastic energy stored in your tendons can produce or contribute up to 35% of your energy needs when running. Sports scientists have studied the change in length of the knee extensor tendon in sprinters and non-athletes. They find, on average, that the sprinters' tendons stretch 41 millimeters, while non-athletes stretch only 33 millimeters. The spring constant for the tendon is the same for both groups, 33 Newton millimeters. What is the difference in maximum stored energy between the sprinters and the non-athletes? Okay, so maximum stored energy. So stored energy, right? So potential energy is what we're trying to find. Okay, we know the equation for springs or potential energy, right? X squared. So now we just have to find the difference between athletes, right? Or sprinters, and then non-athletes. So when we talk about sprinters, this is what they got, right? So we got, so their potential energy equals 1/2. What is a K for sprinter? Well, they're the same for both, right? So it's 33 Newton millimeters. So remember, your K value has to be in meters. So just convert 33 Newton millimeters to meters. So we know that, what is it, 1 millimeter is equal to 0.001 meter, right? So that's 33 divided by 0.001. So that gives us 33, okay, 33,000 Newton meters, okay? Sorry, I said do that math. So now we got a K value of 33,000. X value, it's in millimeters. Okay, so a millimeter, 1 meter is 1,000 millimeters. So you divide that and you get 41. What am I doing? Yeah, so the sprinters are 41, right? So it's 0.041 squared. Okay, so then we get our potential energy, and we calculate that. It's 27.73 joules. And then we have non-athletes. So their potential energy, 1/2. They have the same spring constant, but the distance that they could stretch their tendon is smaller, right? Squared. So now potential energy is 17.96 joules. Okay, so now we just need to find difference. So, simple math, 27.73 minus 17.96. And that'll give us 9.7 joule difference between the athletes and the non-athletes, right? So we see that sprinters, right, they have the ability to stretch their tendons a lot more, probably makes them faster, right? Assuming 35% of your energy, elastic energy stored in your tendons contribute up to 35% of your energy. Yeah. So yeah, they have more elastic energy because they can stretch their heel longer or tendon longer. So kind of interesting, right? So anyways, comment below, sign in, please, if you haven't been signing in. Also, I'm be sending out an evaluation form. If you could fill that out, that'll be very helpful. Even though I'm graduating, I won't be a tutor after this quarter, but say whatever you want. Just let us know, let the department know how you like the videos, basically. And that'll be very helpful in the future if they have to go back and do this again, which they might in the fall. So please fill it out. Tell us how we can improve as a department. Me as a person, talk about that if you want. But again, I'm graduating, so. All right, bye.